Thank you so much for the lovely introduction, Dan. So I'm very glad to be here today. We thought that this topic is very timely. The IPCC just released its new assessment report on 1.5 degrees of warming, and I think actually warning, I could say as well, because it does tell us that we won't have a lot of time left to avoid a climate catastrophe. So currently it looks like we only have 12 years left to avoid some of the worst outcomes of climate change. So that obviously does not leave a lot of time for action, and it also raises a lot of concern around certainly the climate impacts at the moment, and also is a very, very strong call for action. And that certainly includes all sorts of industry sectors, but in particular the fossil fuel sector here, and those companies that have got a lot of assets invested in very fossil fuel intensive industries. So this is definitely prompting the question regarding what is going to happen here to these companies and their assets. We've already seen under the last IPCC 2 degrees of warming discussion that there was concern around that ultimately us trying to limit carbon emissions means that we might no longer be able to extract all current fossil fuel reserves out of the ground. But from a financial point of view, the question is, what does this imply for firm values, and what does this ultimately mean? There have been a lot of discussions here, and you've probably all seen this going through the press a little while ago. The strong warning here by Macquarie. He suggested that fossil fuel investors will lose money, will wreck the market. So very strong warning here that there is a carbon bubble, and ultimately that we might see a strong crash here of fossil fuel stocks. We took that as a starting point for our research on this topic in order to find out what's currently happening here to the valuation of fossil fuel assets. Will we really see a rapid crash now, especially now that we've seen we might limit ourselves to 1.5 degrees of warming, or ultimately is there still a case to be made here for further investment in fossil fuel assets? So our project looked at this question of how many fossil fuel reserves can still be consumed, and there have been a number of papers and a number of reports on this issue previously. So a team of researchers here, Mainshausen and colleagues, they concluded in 2009 that more than half of fossil fuel reserves cannot be consumed, which would mean that we have to leave 50% of what's still in the ground untouched. More recent reports, you see here cited 2015 and 2016, they came to slightly different conclusions. They suggested, okay, if we want to limit warming to 2 degrees Celsius, that 1/3 of oil reserves, 1/2 of gas reserves, and over 80% of coal reserves should remain unused. And then the latest in 2016 concludes quite differently here, that ultimately the proven reserves of fossil fuel firms are only 16% of the remaining carbon budget. So you can see here a lot of debate going on regarding how much can we still consume. The science is definitely urging us to stop fossil fuel consumption as soon as possible and to transition quite rapidly towards a low carbon economy. Here are our main findings. So we actually looked at this question of how effective have we been in terms of action on climate change so far. Our estimation, and I'll show you the methodology behind this in just a few moments, has estimated that so far we probably haven't been fully effective yet in terms of policy action. We think there's only been sort of around 50% of effective action on climate change. When I talk about action on climate change, that ultimately means action coming out of the United Nations COP meetings in regards to actually limiting warming to below 2 degrees of Celsius, and we probably now have to update that to 1.5 degrees. Now, we estimate that the non-stranded asset value of fossil fuel firms is actually pretty close to the current market value. So our research did not find that there is a strong carbon bubble in place and that we have a strong risk of stranded asset at this moment. But obviously, with a more rapid transition to clean energy, that case might now be changing as well. We think that the residual value, so the value after effective action on climate change, is still 91% of the current market value. So in conclusion, it looks like what some of the commentators have said regarding a carbon bubble might be overstated at this point in time. However, this is not saying that there will not be any action here on climate change and that there will not be any action, because we're definitely seeing a very strong transition is happening to cleaner technology at this point in time as well. To give you a bit of an idea here how we arrived at those types of conclusions. So we used a methodology developed by these authors cited here, Barraclough and colleagues, and one of the co-authors sitting in the front row here as well, Tom Smith. They already developed a methodology that allowed to estimate these types of probability of action and also implications on corporate values in a takeover situation. So a slightly different setting. We amended this year to look into those policy outcomes. And we use stock and stock option prices on fossil fuel firms. Our research looked at this issue here over the period from 1996 to 2015. We can certainly now update to factor in more recent events here as well. So ultimately, our methodology here focuses on this particular equation, which is looking into the observed stock price as a sort of weighted probability. So P here being the probability of effective action on climate change if we constrain the amount of carbon used to a level which limits any rise in temperature to below a certain limit. We looked at this from a 2-degree point of warming, but as I said, we can now certainly update to 1.5 degrees of warming, factoring in the recent findings. Then we also look here into ultimately the probability that the stock might actually become stranded and non-stranded. So we've got the expected residual asset value here and also the non-stranded asset value as well in our estimation. If some of you are thinking, wow, this is way too much symbol here, I do have a picture as well with what we actually ended up doing. So you can see here we looked at the traded price of fossil fuel firms, the observed market price, up to each yearly climate meeting. So the United Nations do run yearly conferences looking into policy action on climate change, effective action on climate change. And then ultimately we do have two possible outcomes here. Effective action is taken, effective action is not taken during that meeting, which leads us to potential consequences for the price for the fossil fuel companies sort of over the period of the meeting. We used options on these fossil fuel companies that span the meetings, which means that we actually had the opportunity here to also capture some of this political uncertainty inherent in the meetings. The issue is we do have an equation here that does have a lot of unknowns. And how do we estimate this is the big question here. As I mentioned before, we used call options on the stock of fossil fuel firms. As you can see here, we have made the equation even more complex. So what we decided to do here is to actually express the observed price of a call option with the exercise price X. That's the front bit here written on the fossil fuel company in terms of the probability here. So we have the expected values here of the theoretical values of the call option of the fossil fuel company, conditional on the share price and the volatility. So the share price reflected here, the volatility reflected here as well. So ultimately what we've done is here we used options to complete this particular equation and estimation here, and we reflected the possibility ultimately that the company might become stranded or the stock might become stranded or non-stranded here as well. I think this is probably the important outcome summarized in a figure. You can see the probability of effective policy action over time, and this is tracing each yearly climate change meeting here up to the latest one in 2015. So this gives us essentially almost 21 years of observations. You can sort of see there was like heightened action here. We've also seen action around the Kyoto Protocol and so on. And then more recently, leading up to the Paris Agreement, once again, more stronger action, policy action here as well. So ultimately, what we will probably see now that the IPCC has put out this strong report suggesting that we need to limit ourselves more in terms of policy action, we might actually see an increase here in the probability of effective action on climate change. But to be confirmed by future research findings, so we can hopefully update you in the near future. And here you can also see our estimation in regards to the residual value versus the current market price. In sum, it looks like the fossil fuel companies at the moment are priced relatively close and that to the market price, and that we don't have such a strong carbon bubble happening. However, having said this, our research is also showing that there is currently a rapid transitioning happening to cleaner energy. So it looks like investors have already factored in here the fact that we might see stranded assets happening, and we don't really see evidence that there is such a strong carbon bubble risk. Yes, that concludes already my presentation. So we have investigated whether there are currently carbon bubbles in our markets. We have followed the climate change meetings every year to estimate the probability of effective action, which in the past we thought was around 50%. We have estimated the probability of action, have estimated residual asset values and stranded asset values, and we find that the residual asset value is near the market price. We conclude that at the moment those claims that we have carbon bubbles are overstated. However, having said this, we are seeing a rapid clean energy transition as well, which will accelerate our current transition and which will probably take away also from fossil fuels in general going forward. Okay, that's my part for today.
Should we leave questions till afterwards?
We might actually,
okay.
just in the interest of time.
Great. And then we'll
okay.
Chat afterwards. I'll stay, please.
All right. We need to do a quick change over here in terms of microphone.
It works? No. It should be better like this. One. Right. Hi, everybody. Thanks, Dan, for very nice words about me, and thanks, Abhay, for having me here, and thanks, everybody, for coming. Right, so I'm from as has been said, from Technische Universität Dresden, and I'm originally doing statistics and econometrics, doing a lot of math in there. That's why me with Stephanie, my PhD student, we actually trying to support all this project on the data cleaning, data pre-processing, and methodological part. And Hans Wissmann, he just got the very nice data, and he supported this project with all the economic interpretation. So as it's been seen from the title, we are measuring regional environmental awareness by using internet query data. And this is actually the pretty long-lasting project over the last more than 3 years, and actually ended up in the several papers of ours. So the first thing, when we are thinking about environmental awareness, we are thinking about this kind of picture like here, where we have a lot of dust and a lot of factories working in there. And the question that we raise to ourselves, how they are aware of the environment or the problems with the environment. So we can ask them, but all those questions, all those problems, they are very subjective. So at first, the question that we raised to ourselves, how can we somehow measure using the exogenous variables, using non-direct questionnaires, how can we measure and how can we estimate this environmental awareness? Then the second thing would be, how can we extend the model in analyzing temporal and spatial awareness? How is it spread out? The main idea was around the globe, but we unfortunately cannot get the data for the whole globe, so we just did it for the Russian regions. Then how can we adapt this mass drill data to the from country regions, and how the temperature is mimicking all the things. So because we got the question from the referee that we need to include this as one of the important variables into the model, and whether the situation in the local economy like GDP, GRP can somehow affect or change our perception of the environment. So there were a lot of studies, obviously, studying somehow how people can measure the environment. How can we measure the environmental awareness of the population? In the 60s, there was a personal characteristics. In the 70s, there was some environmental friendly behavior explained in terms of the attitudes measured means of the multi-item scales. Then we have personal value orientation and education and other exogenous variables. So then pretty some time ago, there appears the so-called mimic model, which I go into details a little bit more later on. And they were first used in the practice to construct another index of the air pollution for 122 countries. So pretty similar methodology. So we want to like the index of the environmental awareness of people in the particular region. In the Bünden Nagan, they developed the index of the air pollution. Also not asking, but based on some exogenous variables. So the model was originally developed by Jorichskog and Goldberger in Annals of Statistics in 1975, and there it has been since then pretty actively applied. So in the occupational stress and psychopathology in health professionals, then internal barriers to drug treatment, shadow economy, and so on and so forth. Our main aim is now here somehow to adopt this methodology, this method, in order to measure the environmental awareness. So at first we are looking out for different topics. We can think about the air pollution, about the environmental toxins, climate change, carbon footprint, extreme weather, forest fire, flood, global warming, ice sheet dynamics, and many, many others. Right? So then if we group them pretty nicely, we can group them into several groups, like climate change, which, just purely climate change topics, which can climate change, global warming, temperature records, Arctic shrinkage, greenhouse effect, etc. Then we have the endangered environment, air pollution, environment toxin, extreme weathers. We have the political queries, particular political topics that also somehow connected to the environmental awareness. We have then science, linear geoengineering, ice sheet dynamics, etc. And we have the renewable energies technologies that also related to the environmental awareness. That actually all the things that are people aware of that somehow can Google, if you use this verb, to find in their own search machines to check out what's going on around this or the other topics. So what we did, we actually took those queries, those topics that were listed before, and we have the very pressure data set which contains the monthly internet queries from Yandex. Yandex is a la Google in Russia, where it's actually 50-50 used. It's more than 50% used in rather than Google. And why we use this data, not the Google, because this data we have just exactly number of queries per IP address. So we exactly know from which IP address how many people or how many searches were done for some particular query. Because the author of the first paper, she was working for Yandex, of course, is everything anonymized and is cut to the particular region, but the data is in the absolute values. So it's not normalized like you have in Google. For every month you started from 100 and then it's deviating plus minus. So here we have in the absolute values. So then those columns that I show you in the slide before, these are those queries. These are our variables. These are our indicators. This is somehow how do we react on the environmental changes. If I see something happening, I go to and I Google those things. That's what people are doing, and that is how our indicators look like. So we took them together, climate change queries, endangered environment queries, political, science, and renewable energies. Then we normalize them, number of queries in the given category in given region over the number of all queries in the given region. Right? We discussed also with the scientists from the environmental sciences. They help us to select which queries actually fit to which group. So this are pretty, on one side, pretty subjective, but we try to be as objective as possible. But then, of course, our queries, they are somehow, so our indicators, how do we perceive our changes in the environment, these are somehow dictated by the situation in my region. So in this situation, these are the causes of the environmental awareness. So in this case, we took the regional data about economy. So here are the GRP, workforce shares in different industry sectors, unemployment rate, temperature, emission, the water quality, and so on and so forth. So then, how we bring all the things together? We have the two small equations. One is the measurement part. So our Y, these are our queries. Our eta over here, this is our index, which we do not know. We somehow need to measure, we somehow need to estimate this index. But we believe that what we're looking in our Google, what we're searching on, is somehow heavily depends on this index, right? If the environment is endangered, then I'm looking this thing in my Google. So then this is the model. So now this eta for this ether, we need to put some structure. For that, we need the structural part, which is dependent on the indicators, on our GRP, on the workforce, on the quality of the air, on the quality of the water, and so on and so forth. So we have some kind of two equations. One is the structural part, which model and actually the index. Another one is the measurement part, on which on the left side we have our observations, our queries. So we have a lot of assumptions over here, the normality assumptions, the assumptions on the residuals. If we bring both the equations together, then we are ending up with this pretty simple one. So at first, we have, what do we measure here? We have observations of the y's, we have observations on the x's on the other side. And in order to estimate it properly, we need to standardize, we need to fix, to avoid indeterminacy of the structure parameters, we fix lambda. We put assumptions on the normality. I should mention it here because actually normality is typically violated, which is also in our case, but it's not that easy to adapt the model to some more flexible structures. And we estimated via the maximum likelihood. So how this looks like. So we have our indicator, so what's affecting the model. We have our index, and this is how our index affecting us. So we see there's something going on in the environment, and that's what we are looking in our search engine. So this is how the structure of the whole model. So then if you write it in the formulas, our y's, our lambdas, this is actually how each of the query is affected by the changes of the index, and here are all our models. So we have the deviations in time. Monthly data is stacked, so we have 81 Russian regions, over 25 to 28 time intervals. So in all, we have 2,268 observations. We standardize the data, and for the interpretation purposes, we also standardize and normalize our coefficients lambda. Those. So let's come to some tables. So what we have our coefficients. We considered 6 different models in 1 to M6, which somehow consider different coefficients, different submodels. We see that all coefficients are positive. That's how we estimated them. These are estimation constructions. They are all significant. So how can we interpret each of the coefficient? By the changing of the environment, if our index is changing, it's more affected by the queries, through the queries that are dedicated to the climate change. So something happening, and people are more looking for the climate change queries. They are all of roughly the same level for different models. So the less the people are looking for the political queries if there are the problems with the environment. So this is what we have on the left-hand side, how the index is affecting people's awareness, how the index is affecting people's perception of the changes in the environment. Now what's going on the other side? How all those indices like the mining, like GRP square, etc., how they come into the model. So we extend the model, so these are our beta coefficients, right? So at first we see the GRP per capita and GRP per capita square and even cube, they're all significant, so they are all coming into the model. So this is somehow called like the Kuznets curve, which is telling there should be some parabolic relationship between the GRP and the environment. We have the negative relationship to the temperature. So the worse the temperature, the higher, the more environmentally aware I am. This we'll see also on the later plot, so that's pretty natural if it's becoming very cold, and then Googling what the hell is going on, so I'm trying somehow to find it out what are the problems in the environment. Then we also took into account the climate conference in Paris, because the reviewers asked us, okay, maybe after that period, maybe this was some kind of structural break that actually affected the thing. And after invasion of Russia into Ukraine, we also have the ruble devaluation in this period, which actually also, maybe in this case, not significantly, but affecting this environmental index. So we have far more coefficients. So we have also the education level, share of young people, share of old people. A lot of them are not significant. Some of them are significant, but let's look on the results in the global. So this, we have the map of Russia. We have different colors corresponds to different groups of the environmental index, right? So we have the light blue, so they are the most environmentally aware because the index has the highest value. Then we have in the mid-Russia, we have the lower values, and then we have in this problematic region the lowest environmentally aware the people which are at least searching for the environmental queries in their search engine. So now if we look at on the temporal basis, on the dynamic basis, we have different time intervals over here. We have the average environmental awareness index. We group them all together in order not to plot all 81 regions because we'll have like 81 curves, which will be a lot of noisy. Signal to noise ratio will be not proper here. So we have just 4 clusters over here. So with the cluster with the highest environmental awareness index, the cluster with the second highest, third, and the lowest environmental awareness index. So this is not related to the regions, it is related just to the simple clustering algorithms from the machine learning. And on the right-hand side, we have the average temperature in Celsius in those regions. Actually, we see that they are behaving very similarly with the reverse ordering. So if the index is decreasing, then the temperature is getting higher. The index increased, the temperature is getting lower. We also mark here the rubble devaluation and the climate change conference in Paris. So actually those temperatures and the environmental index, they are behaving pretty close together in this case. So then here we also realize that there is some kind of geographical location, some kind of geographical allocation of all these indices. So if you consider the far eastern Siberia, they have the highest environmental awareness index. Then we go to the western central Siberia, we also go to the southeastern Europe and the northeastern Europe. So we can say that if you're going farther to the east, the more environmentally aware are the people. We took into account the access to the internet. We also took into account for all the temperature issues. So this is, we might say that we try to cover all the indigeneity problems that might arise in this case. So then we considered here, how does the environmental index behave with respect to the GRP per capita? So the more the richer is the region, the more environmentally aware are people in that region. And as expected, we have the negative relation with respect to the average temperature in Celsius. The lower the temperature, the higher is the index. So here we have how the index corresponds to the manufacturing sector. It's again, we have the share of the manufacturing sector. If it's increasing, then people are maybe less aware and they are not looking towards what's going on in the environment. And in the air pollution, we can't say anything, so they are really independent in this case. And also the coefficient was almost insignificant in our study. So now the last two slides that I'm showing here. So here is the changes. So we have on the weeks axis in this plot, we have the awareness index for year 2014. Here we have for year 2015. So when we see that actually all the points are lying very close to the main diagonal, which is an indicator that actually if the region was environmentally aware, it stays environmentally aware. If it was not environmentally aware, so it was like 40, for example, stays perfectly on the line, so it was not environmentally aware, and it stays not environmentally aware. So if you have like 14, in year 2014 it was not environmentally aware, but it becomes pretty well, it's going pretty well in year 2015. What we have on the right-hand side, so we would like somehow to see whether what we are measuring is somehow has some economic sense instead of just telling the stories around the data. In this case, we took the investment index and we also have the colors from the environmental investment risks that are measured externally, and we got the data from the Russian Statistical Fund. So we actually see that there is the negative relationship, so the less environmentally friendly people, the less investments they are getting. And also the colors, so here we have the higher investment risk is the red color, and the index is high, and the lower investment risk, then the index is pretty low. So then let's go to the concluding remarks. So we try to explain the latent variable region environmental awareness of 81 Russian regions by the MIMIC model. We include the monthly internet queries from the Yandex as indicators, and we took the regional characteristics as cost variables into account. So we hope we capture the seasonality by the temperature, and also the highest environmental awareness index is the coldest and the richest regions as somehow is to be expected. And so what we would like to do, so if longer time series will measure some significant trend in the environmental index, this we don't know, we are gathering more and more data. That's it, and I thank you for your attention. And if you have some questions, then we have the Q&A session, right? Thanks a lot.